Good morning from Kyiv, Ukraine, from exactly the Motherland Monument. They call it the Motherland because the city of Kyiv, known as Kievan Rus, is the birthplace of the Slavic nation, Belarus, Russians and Ukrainians. This is where their story started. This monument does not symbolize that, it commemorates what they call the Patriotic War, which is the Second World War. More than 7 million people lost their lives during the Patriotic War. So this monument is of a big significance to the Ukrainians. Some agree with it, some even want to take it off. Why? Because the shield that you see there carries the Soviet emblem, and usually the Soviet stuff are not always welcomed here. So if you are ready, I'm ready to teach you nuclear reaction. So I was kicked out from near the Motherland monument because apparently I need an authorization to record from there. With the phone is okay, but with the camera is not okay. I don't know who has to give me this authorization. I'm outside the territory that you see is there. So let's start with atoms. Atoms are the smallest unit that form matter. Whether it's liquid, solid or gas, they are made of atoms. So it's the smallest unit that we know. Now, before we even start to talk about atom, where does this come from? So the first guys to notice, or even I would say to have this principle, this thought of atom, were, again, you guessed it, the Greeks. There was a guy called Democritus, like democracy, but has nothing to do with it. He was a Greek philosopher, even before Socrates. So he was the first one to formulate an idea of an atomic structure of the world in which we live, made of like small particles. So he was the first one to formulate this idea. We're talking about the year 400, 300 BC. So that's like more than 2,300 years ago. So from this time until 1803, there was a British guy called James Dalton. So John Dalton put his ideas based on Democritus principles. He completed them saying that atoms are indivisible, they're indestructible, like you cannot destroy them. He also said that matter is made of different types of atoms, they combine themselves, then they form other type of molecules, etc, etc, etc. Niels Bohr, Schrödinger, Heisenberg, Chadwick, all of them furthered that model to come to this one that I'm gonna draw for you. So this is the model of the atom, how the atom looks like. So you have mainly two parts of the atom. So you have the core of it, and then you have an orbit where the electrons orbit around that core. So the core, I'm going to use two colors to draw the core. So the core is made of, so this is half part of the core, the other part. So I'm trying to give it a circular shape. What you see here in green and here in red are the elements that constitute the core of the atom. We call it the nucleus. So this one, all of it is nucleus. The red ones are what we call the protons. The green ones, neutrons. This atom that you see here, this is the core of it, the nucleus. Then, as we said, you'll have the orbit. Let's draw it with the yellow one. The orbits that I just draw here, they represent the movement of the electrons, because on top of the core of the atom, the nucleus, there are electrons orbiting around it. So just symbolically, I'm gonna draw an electron here, electron here. So this, we said, it's the nucleus, and these are the electrons. So this is the model of the atom. You have the nucleus in the middle. The nucleus is made of two parts, protons, neutrons, and around it, electrons are orbiting. Let me just give you a little tip. You see these letters P, N, E here, electrons, neutrons, protons. So we know that the electron is negative, right? So usually the symbol is E minus, right? So the charge of the electron is negative. Let's take the example of uranium atom, since we're talking about nuclear fission. Let's say this one is uranium 235, 92, and I'll explain to you what are these numbers. This, when I wrote it here, I didn't put plus. The fact that I didn't put plus, that means that electrically speaking, the uranium atom is neutral. It does not carry electricity. On top of that, we know that the uranium, since it's an atom, have some electrons. But how comes the final atom is not charged? There is no electricity around it. Well, that's simply because there is someone to balance that negative charge of the electrons, and that someone is the protons. So the letter P here means that the protons are positively charged. So the electrons are negatively charged, the protons are positively charged. So the quantity you have here in protons will be equal to the quantity of electrons. If I have 10 electrons, I need to have 10 protons, so that at the end of the story, the atom, the electric charge of the atom is neutral. But here I don't have 10 electrons. Why? Because the symbol of the uranium says 235, 92. You see the 92 here? That is the number of protons. So therefore, by deduction, I know that the electrons are also 92. Otherwise, the uranium would have been electrically charged. The 235 is simply the quantity of protons plus neutrons. You see the 235 here is what you call the mass. It's kind of how many protons add neutrons. So we have two, you see what I draw here? The totality of it is 235. So if I want to deduct the number of the neutrons, I simply have to do 235 minus 92. Again, 92 being the number of protons. It will give me 143 what? Neutrons. So you could already see something, that this was just symbolic. The quantity of the neutrons is way higher than the quantity of the protons. 143 neutrons versus 92 protons. So this is the atomic symbol. It's the symbol of the atom. In this case, we took the example of the uranium. The star of today is uranium, and there are many uranium atoms, but the one we are getting interested into is 235. The letter U that you see here, this is the chemical name, right? So if you look at the periodic table, the Mendeleev table, you'll see that uranium has the symbol U, which is its name. This one is what we call the atomic number. We know that the atomic number is equal to the number of protons. Since uranium is electrically neutral, that is why I did not write plus. I didn't say U plus. If I would have said U plus or U minus, then it has an electric charge. This is neutral, therefore the number of protons is equal to the number of electrons. Protons are positive, that is why there is the letter P, protons. Electrons are negative. So 92 protons means I have also 92 electrons. The last one is this one, 235. Is the sum of the protons plus neutrons. So the first one is U, is the chemical name. This one is what we call the atomic number. We know that it's exactly equal to the number of protons. This one is what we call the mass number. So the mass number is the sum of protons and neutrons, like, you know, the mass of that nucleus, like how many protons and neutrons do I have. So this is the basic symbol of atom. Enrico Fermi, an Italian in Rome, he was the first one to bombard uranium with neutrons. So the neutrons was already discovered. This one, think of it, a lot of things were discovered step by step. So he bombarded an atom of uranium by neutron, and then he discovered that it's split into two things. Many have disagreed with the experiment results of Enrico Fermi. They disagreed with what he obtained, but there is a group of 4 people: Otto Hahn, Strassmann, Lise Meitner, and the other one is Fritz. They worked for 4 years. They concluded on the experiment that Enrico Fermi did, and they even confirmed it's a nuclear fission. What happened? That means that when he bombarded them with the neutron, he has split the nucleus of the atom. They even identified the resulting particles, because this is where it gets interesting, the difference between a chemical reaction and a nuclear reaction. So let's take uranium, we'll call it U. 235. So this is the uranium atom, and I'm gonna throw at it a neutron. So there is a neutron that will bombard this atom. If I do this, what's gonna happen is that the uranium 235 will become uranium 236. So here I created a new element, but what's gonna happen to this one? It's gonna split into 2 new elements that have nothing to do with uranium. And that is the difference with the chemical reaction, because when you look at a chemical equation from one side and the other side, and you look at the elements that make the first side of the equation and the second one, they are the same element. You do not go from, I don't know, copper to iron like this by magic. It doesn't work like that. But here you form 2 new elements. So we said from uranium 235 I obtained uranium 236. This element here, what's interesting, it cannot accept to stay in this state. It will split to form two new elements. One is called krypton and one is called barium. The interesting part is the following. With the split of the uranium atom, what happens is that energy was released in form of heat. So this energy, we can use it for our daily purposes. Not only that, this uranium atom, after it splits, it will also release randomly between 2 or maybe 3 neutrons. This is really interesting. That means that not only this split creates the energy for me, but it creates also other elements that can start the same process with another uranium atom, which means is that if here I have another uranium atom, just like the first one, uranium 235, if this neutron hits this one, I can start the same process. That's why we call it reaction in chain. So now that you have these elements, you can already kind of guess practical uses of these. Yes, civil nuclear reactors, nuclear bomb, etc., etc. Before we go to that part of like practical use of it, etc., I just want to give you a second thought or second explanation of the nuclear power and where that heat comes from. Here is one thing I want to tell you. If you look at the mass, this is uranium atom, right? Let's say uranium 235. When you look at this mass and you say, okay, I want to know what's the mass of this whole atom, you will notice something, that the mass of the whole atom should be the sum of the mass of the individual particles that form that atom, which means that if the mass of the atom, let's call it Ma, is this one, well, you want it to be equal to the mass of the protons plus the mass of the neutrons plus the mass of the electrons, right? So you sum all of this and you have the final mass of the atom. When you sum these elements that constitute the atom, the weight of them, when you sum the mass of the elements that constitute the atom, it will not be equal to the total mass of the atom. It will be under. The mass here of each individual particle is under the total mass. So then you will tell me, hold on, what is the gap? What is the difference? The difference is this energy that you see here. So you are telling me, hold on, energy has weight, has a mass. Of course energy has mass because there is another man, Albert Einstein, if I'm not mistaken, 1905, he published his document where he stated to the entire planet something that looked like science fiction or even madness or even nonsense, where he said that the energy E is equal to mc power 2. Energy is equal to the mass, speed of light power 2. This is a simple equation that put a direct link between energy and a mass. So that mass that was missing here, because now this one is not a sign like this anymore. So if you sum up the weight of each particle that constitute the atom plus a certain energy, then in this case you find the total mass of the atom. This is not very intuitive because it's like if I tell you what's the mass of a car. If I ask you what's the mass of a car, you will tell me it's the sum of the mass of each individual part that makes that car. Take the wheel, the engine, the seats, weight each one of them, make a sum, addition them, and then it gives you the total mass of the car. It makes total sense. That's not the case for an atom because there is a missing part, which is energy. And this missing part, this energy here that we have, is what we release when we do the nuclear fission. You see, that's like that's why Enrico Fermi, when he made that experiment, he noticed that the resulting particles, the weight of them were not equal to the initial weight of uranium 235. It's like if this one, let's say, I'm just throwing a number, let's say this one is weighted 1 gram. He started this experiment, let's say, with 1 gram of uranium, and then he resulted, I don't know, in 0.9 gram of resulting elements. He said, hold on, I lost 0.01 gram. Where did this go? Well, that 0.1 gram, it's transformed into energy. That's what Albert Einstein stated in his document in 1905 when he put a relation between energy and mass. And Albert Einstein didn't make an experiment to demonstrate this, but his brain worked in a different way. That's all I can say. So why the nuclear reaction release energy? E equal to mc power 2 is because when we split the uranium atom, part of the mass of the atom is converted into energy. That energy is what we use to heat the water, which in turn convert water into steam. We send that steam on a turbine. The turbine rotates the generator. I explained all of that process in my previous video. The link to it will appear here at the top right corner of the screen. This is one way to see it using Albert Einstein equation. I want to give you another way, a third way to see it, and that third way is related to the nuclear force, because in general there are 4 forms of forces. The first one is what you call the gravity force. So when you look at planets and stars, what binds them together is gravity force. That's the first one. Has nothing to do with us here. It's not our business. The second one is magnetic force. So for a lot of chemical reactions, that force gets involved. And the third and fourth one is nuclear force. There is like weak and then strong nuclear force. Doesn't matter here, like the difference for what we are trying to explain. So the nuclear force is happening at the level, the smallest level you can imagine, which is the atom. Not only that, it's happening at the level of the nucleus, which is the core of the atom. What's happening here? So now you got the fundamental idea of how a nuclear fission happens, but more importantly, where does energy comes from? To summarize, the energy that is released either in a nuclear bomb or in a civil nuclear reactor, that energy, when you look at down, when you boil it down to the principles, the fundamentals, you go to the nucleus of the atom, which is the core of the atom, which is made of protons, neutrons. We see that protons are positive, neutrons are neutral, but yet they are still together forming one piece. Knowing that the protons are positive, we know that they will push each other, because plus and plus will simply push away. It's like a magnet, north, north, south, south, they will push each other. But in this case here, they are still forming one piece, not pushing each other, because there is another force called nuclear force, which is keeping this nucleus together. And that nuclear force is what we release, whether in a bomb, to destroy, to devastate. That's the case of Hiroshima and Nagasaki. Or in the case of a civil reactor, we use the energy that was stored in the form of nuclear force, we use it to release heat, because we split the atom, we split in fact the nucleus of the atom. This is interesting, the result of a nuclear reaction. It's not like a chemical reaction. When you look at a chemical reaction, you remember one part of the equation, the other part, the elements that constitute, the individual elements that constitute one part of the chemical equation are exactly the same on the other side of the equation. So we did not split atoms here. But in the case of nuclear reaction, look, I went from uranium and I resulted in barium and krypton. Barium, krypton have nothing to do with uranium. It's 2 different elements, so I create new elements. That's the fundamental difference between a nuclear reaction and a chemical reaction. And along the way, I created heat. More importantly, I created other neutrons that will be used to hit another uranium atom. So here, I have to initiate the process and bombard uranium with neutron, but once I split the first one, the process will sustain itself. That's why we call it reaction in chain, which will bring us to the practical use of it. Now we know that you can extract heat. We don't know how much heat it is, how powerful, how much can we use it in practical use. We will go in our next video to the practical use of nuclear reaction. Since I'm a peaceful man, I'm not gonna dig into the nuclear bomb, but I'm more gonna dig into the civil use, peaceful civil use of nuclear reaction, which is known as nuclear power plant, like many of them that we have around the world. This has been said, my friends. I hope that you enjoyed this basic explanation. In the next video, we will look at the details of this reaction in terms of values. What's the speed of these neutrons that are created? What's the speed of the initial neutron? Are they from the same speed? I can tell you absolutely not. The speed of these ones are a million times higher than the speed of this neutron, but yet we have a civil controlled reaction in a power plant. Nothing explodes, with the exception of Chernobyl, which we will see later on. And we will also quantify, and this is where it gets interesting, the energy that is released here. How much is it? Why do I have to go into this radioactivity, a lot of risks, when I can just burn coal? Why should I go through that? I'll show you the advantage of nuclear reaction, civil nuclear reaction. I'm not here to convince you that nuclear reaction is good or bad. That's on you. You gotta make your own opinion. You gotta influence your own politics in your country by the power of vote. That's not my job, that's yours. My job here is simply to expose the facts and to compare a civil nuclear reaction to burning coal and producing electricity with it, compare the amount of energy, the value that you will see, and the difference are insanely big, are mind-blowing. So I just can imagine at the time in the 30s, 40s, when they saw the difference of energy. Even in Chernobyl, 1986, what happens in Chernobyl, this is no, it's impossible. A nuclear reactor cannot burn. It's mind-blowing. This science is fascinating because we are acting at the level of the nucleus, which is not only the atom, but the core of the atom is even smaller than that. If we split it, we can release energy and do a lot of fun stuff. This has been said, my friends. Did I just say my stuff? I thank you very much for watching this video. Please, if you like it, click on the like button. See you later, my friends.